Section 7 on explainability. My name's Giles, but I am going to basically follow the lead of everybody else and get out of the way and keep time.
Great. Thank you. Hi, everyone. My name is Berk Ustun, and this is work with Alex Spangher and Yang Liu. So let me start off with a hypothetical. Say that you recently bought a house, you're a little short on cash, you apply for a loan online, and you're denied. Do you know what you can do to be approved? So these days, the answer is no, and that's because we're increasingly using machine learning to make these types of decisions, and the models are making the decisions using all sorts of variables, like the type of phone that you're using or your personality profile. Now, obviously, this makes it hard to figure out what you can do to get a loan, but what's more surprising is that when a model uses immutable attributes, like your personality profile, where there's going to be a chance that it weighs it so heavily that you can't do anything to get approved. So in our paper, we frame this using a concept that we call recourse. And recourse is your ability to obtain a desired prediction by changing actionable input variables. So things like your income and your savings as opposed to your personality and your age. Now, this is a session on explainability, but recourse is not explainability. We are not asking, why did a model make this prediction? Is this a meaningful reason? We're asking, what can be done to change the prediction? Does there exist any feasible action? And that's an important question to ask because, well, I mean, if you're denied a loan, there should be something that you can change to get approved. If you can't, then you will always be denied the loan. And what the model has done is that it's stripped away your ability to improve your own creditworthiness. So in this sense, recourse represents your agency in the model's decision-making process. And that's something that's important when machine learning is used in areas like lending, like hiring, like insurance. So it turns out that even the simplest, most transparent models may not provide recourse. And that's because they use variables that aren't actionable. Sometimes this might be things that are immutable, like your personality type. It could be variables that can be changed at some values but not others, like if you have a PhD. And it could be variables that you shouldn't have to switch, like the type of phone that you're using or whether you're married. Now, sometimes these variables will be governed by regulations, but that's not true in all countries and in all applications where recourse is relevant. And I mean, more broadly, it's hard to regulate this by controlling the types of variables that are used in prediction. And that's because small differences in variable encoding could make something immutable. It could be that variables that are required for recourse are missing in the deployment population. And the last thing is, a model could only use actionable variables, but still require drastic changes to get approved. Like, a model could say, we'll give you the loan, but you've got to increase your income by $1 million. So, I mean, in light of this, it's important to look at the feasibility of recourse as well as the difficulty of recourse, and to do this in the context of the population where the model is being deployed. So in our paper, we present methods and software to do this for linear classification models. Our tools allow you to do this without interfering in model development, and they let you answer questions like, what can a person change to be approved for a loan? What is the feasibility and difficulty of recourse of a model over a certain population? So both of our tools use a very simple optimization-based routine. What this thing does is that it checks recourse for a single person. It will take in the classification model, the input data for a certain person. There's supposed to be a little person emoji there, and a set of valid actions for that person. It will then solve an optimization problem, and it will spit out either an action that flips the prediction for that person, or definitive proof that the person does not have recourse. So what you need to know here is that what's actually hard is proving that someone doesn't have recourse, because that requires you in this setting to go through all the actions and make sure that none of them flip the prediction. What else do you need to know? Well, this routine, we can do it for all data types in a way that is fast, and that supports specialized cost functions. And what these things do is that if a person has recourse, well, then they allow you to choose between different actions, and then also measure other quantities of interest with regards to recourse. So how do we use this thing? Well, the first way that we use it is to build what's called a flip set. So a flip set is a list of actions that someone can take in order to flip the prediction of a classification model. So here we just run our routine several times and enumerate different actions that will flip the prediction. Here we've done this 4 times. We've created a flip set with 4 items. Each item shows a set of variables that can be changed and shows their current values and the values that are needed in order to flip the prediction. So here you see that this person could have been approved for a loan if they had paid $790 last month. And in this case, it's important to create flip sets with multiple items if you really care about recourse, because any one of these things could be infeasible for the person who's receiving it. Now, the second way that we use this is to do what's called a recourse audit. So here we're trying to measure the feasibility and the difficulty of recourse in a population of interest. And what I'm showing you here are just standard performance plots for logistic regression models that are built using the UCI credit dataset. So here there are 10 logistic regression models at different L1 penalties. Each model is represented by a dot. As we increase the L1 penalty, the accuracy changes and there are fewer variables. So in this case, what a practitioner could do is to run an audit for each model using either training data or data from their target population. And that would produce graphs like this. So what's being done here? Well, for each model, we look at everyone who's denied credit. We then run our routine for each one of those people. We check if they have recourse, and we get an estimate of the cost of recourse. And here, on the left, I'm just showing you the percentage of people who have recourse, and I see that as the models become sparser, we have less and less recourse. And on the right, I'm showing the cost of recourse. So these are violin plots that show the distribution of costs in the target population. And here we've used a specialized cost function so that this actually represents something that's meaningful. So in this case, for instance, a cost of 0.4 means that a person needs to change, needs at least a 40 percentile shift in any variable to flip their prediction. And that's not like an end-all, be-all measure of difficulty, but it's something that's communicable and that accounts for the target population. So I'll end by talking a little bit about explainability, since it's often brought up as a tool for consumer protection in machine learning. And I'll say that explanations are useful when you want to understand or troubleshoot a black box model, but they don't provide good consumer protection in areas like loan approval and hiring. And that's because they don't produce information that's actionable or contestable. Now, recourse isn't explainability. We're asking a different type of question that's designed to mitigate a specific type of harm. But by doing this, we're producing information that is actionable, that is contestable, and providing several avenues for regulation. Like practitioners could audit models for recourse. This could also be done by third-party agencies or during model procurement. And consumers could be sent flip sets to figure out what they can do to obtain desired predictions. And I think more broadly, the key takeaway from our work is we can provide much stronger protections in areas like loan approval, like hiring, by going beyond explainability and coming up with concepts that are designed to mitigate specific types of harm. Thank you.
Hi everyone, my name is Smitha. I'm a PhD student at Berkeley, and I'll be talking to you about our work on model reconstruction from model explanations. So in recent years, there's been this huge surge of demand for explanations of the decisions made by machine learning models. And a lot of where this demand comes from is concern around the validity of decisions made by secret, black box, often proprietary models. For example, if you get rejected for a job by a machine learning classifier, you want to know why. You want to make sure that it wasn't because of your race or your gender or some YouTube video you watched 3 months ago. So generally the hope for explanations in these kinds of settings is that they will shed light on some of these problematic cases by revealing some information about the model to us. What we show in our work is that model explanations can actually reveal a lot more than you might expect. In fact, they can reveal the whole model itself. What I mean by that is that we show that you can reconstruct or reverse engineer models from a broad class of model explanations. Why does this matter? Well, it matters because model leakage can have a lot of negative downstream effects. For example, it can compromise privacy in the sense that once you have the model, it's often possible to reconstruct training data, which is of course problematic for sensitive domains like medicine. It can facilitate gaming. Once I know that this job model highly weights the number of GitHub repositories I have, I can just open 1,000 of them. And of course, it can leak IP. So taken together, these are all basically practical challenges that any, say, company that is considering providing explanations will be hesitant to actually do so. So having that said, as an overview of what we've worked on, let's delve a little bit deeper into what we actually did. So what is a model explanation? Of course, there's many proposals out there for what an explanation could be. But many of the most popular sorts of explanations that have been considered in the machine learning community are based on the gradient of the model F with respect to the input X. This comes up when you're looking for feature sensitivity, when you're trying to do linear approximations, and it also comes up in a popular class of methods in computer vision known as saliency maps. So in this example I'm showing you, there's some model that's trying to classify this bird. And on the bottom row are saliency map images that are supposed to sort of encode which features or pixels were most important for the classification, as in the darker pixels had more influence on the decision made. As you can see, there's many types of saliency map techniques out there, but they all are essentially some kind of post-processing on the gradient. So for our work, we're going to abstract out the underlying primitive and just consider explanations that are the gradient. So let's just fast forward and imagine that we tried to use these kinds of explanations in practice. So for example, let's say some sort of cloud service like Google Cloud, which currently allows you to send it an image and get back a classification, now not only sends you back a classification, but also this gradient explanation. After sending a few images, you actually have quite a lot of data. You have labels on all these images, as well as this gradient explanation of why the model supposedly made the decision. So our question is then, can we actually just reconstruct the model from enough queries to this API? We're going to look at this question first in theory, then in practice, and end with some of the broader implications of our findings. So first off, to analyze this in theory, we can actually abstract this out into a nice learning problem, where the learner gets to query the API with some input x and get back both the valuation f of x as well as the gradient of f of x with respect to the input x. Our question then is, how many queries do we need to reconstruct f? And in particular, we'll be interested in the speed up we get from having access to the gradient, because we want to understand what implication, how providing these explanations affects the capacity to reconstruct models. So as a warm-up, let's just look at the sort of simple linear case. Suppose f of x equals w transpose x, a linear function with weight vector w. So how many function evaluations would we need to reconstruct the model? In this case, reconstruction simply amounts to figuring out what the weight vector W is. Well, we would need dimension D, where D is the dimension of the input vector and the weight vector, because after D queries, we have D linear equations, and we can just solve for W. How many gradient queries do we need? Well, just one, right? Because the gradient of f of x with respect to x is the weight vector W. So in this case, the gradient actually reveals the model immediately. So the simple case is just to illustrate to you that actually the gradients can give you a lot of information about the model potentially. To move to a slightly harder case, we looked at reconstructing a one hidden layer value network, which has generally been a challenging stepping stone towards analyzing more complex networks. We find that, again, here you get basically a speed up on the order of the dimension D. We give in the paper a near optimal algorithm that's sort of a randomized binary search that I can't go into, but I encourage you to look at the paper for that. Of course, in practice, we use far more complex models. So we also give a simple heuristic for reconstructing models, and we test it out on standard image classification benchmarks. So in particular, we're going to again have our unknown proprietary model F. We're going to have a model that we train using queries to the API F hat, and there's going to be two types of losses that we train F hat with. First is a loss on the gradient queries that basically just makes the gradients of F similar to the gradients of F hat. The second is a loss on the function evaluations that makes their function evaluations similar. And then we minimize a trade-off between these two losses. So surprisingly, this really simple heuristic actually does quite well. So we tested this out in different settings, which varied how much information the person trying to reconstruct the model has. In the simplest case, the person reconstructing the model knows the architecture of the proprietary model and also knows sort of the kind of data that it was trained on. In this case, we get a 10 to 1000x speed up. But of course, this might be a little bit unrealistic. We might not actually know the model class of the proprietary model. In that setting, we find that we still get about a 10 to 100x speed up if the model class that we, the reconstructor, are using is larger than the model class of the proprietary model, which makes sense because you get a bit slower, but you can still learn it. And then lastly, of course, we might not actually know the sort of data that the proprietary model was trained on. And we did something very conservative here because we might not know that it was MNIST-like or CFAR-like, but we might still know that they were images. We actually tested, well, what happens if we just query random Gaussian noise? There we can still get a 1000x speed up on MNIST, which is actually surprisingly better than when we were using the MNIST-like images. With CFAR, it's really hard to learn either using function evaluations or gradients with Gaussian queries because it's more complex, and so that kind of makes sense. The last box we didn't look at. And then, all right, so what are the implications of these findings? Well, the key takeaway here is that there is a tension between explanations and model secrecy that might pose a practical challenge to deploying explanations in the real world. On the one hand, we want explanations because we don't trust secret proprietary models. But on the other hand, if explanations reveal too much of the model, this is going to pose a real challenge to get any sort of company to actually adopt explanations. So we have to think about this kind of consideration. For future work, there's a lot of directions. First of all, are there explanations that are useful for something we want explanations for, but don't reveal the entire model? This is actually a very nuanced question because it requires us to, one, know what we want explanations for, and two, know what kinds of negative side effects we're trying to avoid via those questions, and then the burden is to show that we get the former without the latter. And then lastly, when we think about what we want, Deirdre mentioned in her keynote earlier this notion of contestability. Maybe we actually want contestability rather than explainability. And when we look at this sort of broader notion of what we want, maybe we don't actually need explanations as formulated as an intermediary. Maybe there's a more direct way to get to contestability through more clever systems of accountability. And with that, I'd like to thank my collaborators, Ludwig, Schmidt, Anca, Dragan, and Moritz, Hardt, and I'm happy to take questions at the end, or if you find me later. Thank you.
Great. Okay. So what I'm going to talk about is, in many ways, it's a sister paper to the stuff on actionable recourse. So I'm interested in the problem of explainability. In particular, I'm interested in something we call counterfactual explanations. which are explanations that take the form like, you were denied a loan because your annual income was around 30K. And if instead your income had been 45K, you would have been offered a loan. And this is something we sort of like came up with last year, and we've sort of like gone through. It's now part of TensorFlow in the What If tool, so you can play with it. And so why are these kind of explanations useful? And like, why do we actually want explanations? So what we did in the original papers, we went through and say explanations are helpful for three things, right? They let you understand why decisions happen. They let you alter future decisions, which is what's been talked about in the Recourse paper. And they allow you to challenge future decisions. And we said counterfactuals do this. And like, okay, we can believe that. So let's give an example and go through why this is the case. So suppose you have a fully automated system, a security guard of some kind. You go, right, okay, I'm going to put this in practice. I'm going to deploy the system and see what happens. You're faced with unexpected behavior. Something goes wrong. And then you're like, well, I don't really know much about robots, but how can I fix this? And you turn around and you go, well, can we understand the behavior using counterfactuals? So we say, if the robot had seen the edge, would it have stayed out of the pond? Or maybe if no one had pushed the robot in, it would have stayed out of the pond. So you can actually start like ignoring, like, what does a robot do? You can figure out what's going on. This gives you actionable behavior. You're like, I can put tape down. I can mark the edge of the fountain. I can keep it out. I can hire a real security guard who will follow my fake robot round and stop people pushing them in the pond. And at the same time, you can turn around, you can challenge the system and go, I can't keep the robot out of the system. This isn't good enough. This doesn't work in the way it should. I'll send it back. So the key point is that you do not need to understand how a robot works. You don't need to know the computer vision. You don't need to know the control system in order to know what's important. And so what we did is we turned this into a practical algorithm. And because I've been told I have to gloss over all the technical details, the important thing is that for neural networks, we solve this using exactly the same methods you use to train it with. And this is something concrete. You use backpropagation, gradient descent, and you can find counterfactuals. You can find the closest possible world in which the outcome you wanted happened. Okay, great. So that was the previous work. And now what we want to do is we want to build something for data science. And out in the real world, what people generally have is a very simple classifiers. They have logistic regression, they have linear regression, they have SVM, and they have very ugly data that doesn't really make sense. So you go through and you're like, okay, well, my credit score is based on some measure of like my personal debt. And this is like, scores like 7 or 84. And it also has like occasional values where data is missing or the data is expired. Like the last time this was measured, it was too long ago to use it. And what data scientists, what statisticians and actuaries do is they do a very simple one-hot encoding where you take the data. So you go through and you go, okay, well, if it's missing or if it's expired, I'll just put a dummy value in. I'll put 0 in. And I will create 2 more columns. And these will take value 1 if the data is missing, and it will take value 1 in the other column if it's just expired. And then basically all they do is they just train the linear classifier of choice on top of this. And that's pretty much it. Job done. You then go away, you try something more complicated. But in practice, this works really well, and people just keep coming back to the linear classifiers. And our idea was simple. It's just like, well, when we create the counterfactuals, which we talked about earlier, we just do this in the encoded space. And this naturally lets us handle problems where you have not just continuous data, but this weird mix of continuous and categorical, where things are flickering on and off and disappearing. So you go through and technically you create new binary variables, and you say V1 is just saying, is this valid data or not? V2 and V3 are saying, is it missing data, is it expired? And you just say, one of these must always be on. You go through, and then what we did is we took the previous objective, which was this Lagrangian formulation, and we transformed it into a linear program. And this, for what it's worth, is exactly like Lewis's formulation of counterfactuals. It's saying, find the closest possible world, find the closest data in which we have the outcome we want. And this you can just write down, and you can solve with previous constraints as a mixed integer program. And at the same time, we went, well, what we really need is diverse explanations. So if I give you a counterfactual and I say, well, if your outcome had, if you want 45K instead of 30K, you've got the loan. So that's great. But I could have also said, if you'd asked for less money, if you'd asked for 15K instead of 10K, I would have given you the loan. And this is, this is actionable. This is something you can go, actually, one of these explanations is useful in a way that the other one isn't, but you don't know which without knowing the person who's asking. In order to get these diverse explanations, what we do is we make use of the fact that our counterfactuals are sparse. So that every time we try and generate a new explanation, we try and change as few variables as possible. And what this means is that to create a new one, we can just fix the previous values which we changed, and then go through, we run the optimization again, and we find a new solution. And when this fails, you can just roll back constraints. Okay, and so what does this look like in practice? On the left, you can see some explanations that we generated using the previous method. And it's on this old legal data set. It's trying to predict how well people are going to do in their second year of law school, I think, and if they'll get over average or under average. And what we found, the first time when we wrote the original paper, was that everything looked fine. So this is a very old, very racially biased data set. And when you train standard algorithms on it, linear classifier, they learn to be racist. They just mirror the data. And so you got explanations which said, for a black person, if your LSAT had been slightly higher and you were white, we would have given you an average score. And this is not an actionable explanation in the sense that the other guys were talking about. This is exactly the kind of thing people need to know. Right? When you write a system, if you get back an explanation like this and it tells you something has gone horrifically wrong, and we're giving these kind of explanations to people, you're like, I have to go back, I have to actually fix what's broken in the system. If you give this to people out in the world, they can't change their race, but they can kick up hell, right? They can create enough attention, and they can actually force people to change the system in a way that isn't changed otherwise. So anyway, what we found in the original paper is the classifier was biased, and it was racist against black people, and we simply didn't realize the first time we ran this through, because maybe less than 10% of the population were black in this, and the samples we generated were all for white people, and it just said, it didn't try and, the counterfactual never said change your race. It always said, oh, do better or worse in the law school in order to get an average thing. So we actually had to go and find it in order to realize that it was racist. Now with the diverse ones, this becomes immediately apparent. You take someone who's white and doing better than average, and it says, yeah, you did well, but if I thought you were black, I would have said you were going to fail. And it gives people a chance to realize how broken the system is. It makes it much clearer and much more obvious what's going on. When applying it to, I guess, less biased data, and looking at financial records and stuff, quite often it's like, why are you not being approved a loan? And we can now give people 20 or more than 10 different explanations for you're almost there. We can almost fix what's wrong with your credit score. And here's many different paths you can take to try and fix it and to understand what's going on. And quite often, so it's great when you're right at the boundary, and sometimes this fails, and in the same way the guy was finding there are no actionable recourses, sometimes you may only get one possible counterfactual, and it says, we are missing your external risk estimate, and without this you will always be predicted that you should not be given a loan. The only thing you can do is go away and get someone to give you an external risk estimate. This can be contrasted with the linear explanations that people were just talking about. So this is normally what people think of as an explanation, right? And it's just basically this big list of weights. And going through and as someone who perhaps doesn't understand maths, it's what would can you would you be able to make sense of this? And would you be able to do something with this kind of explanation? So yeah, just to wrap up, what we came up with was a method for generating exact counterfactuals for the most common classifiers. This avoids a bunch of technical issues with local minima, stability, and thresholding issues that we had from the previous approach. This lets us handle these weird mixed sort of data which has a discrete and continuous variables in a unified framework, and we have code available. Thank you.
Hi, I'm Vivian, and I'm a PhD student at the University of Colorado Boulder. Actually, it's supposed to be this slide, but it's okay. This is a joint work with my advisor, Chenhao, and today I'll be telling you more how machine assistants affect the human decision-making process. I'm sure most of you have already seen or heard this article written by ProPublica. Since its online publication, it has now become a classic case in understanding fairness in algorithms. It has caused much controversy after its online publication because it claims that the tool is against African Americans. In this slide shows these two people, Vernon Prater and Brescia Borton. Both of them committed petty crimes, but Borton on the right is classified as a high risk as compared to Prater. Most previous studies assume that these tools, such as Compass, they are used in real life without any human intervention. As such, they are concerned with the impact of such tools when used in full automation. However, this is not the case in reality. In 2017, the Wisconsin Supreme Court ruled that judges must take account of the algorithm's limitations into consideration when considering someone's sentence. So given all we have talked, we know that full automation is not desired. A natural question to consider and think about is how judges make decisions with Compass. And also, what can we add to make the predictions more interpretable to humans? For example, in the Compass example, the Compass tool only provides a risk score. But what if we were to add on explanations to the predictions? Would it be more interpretable to humans then? So given full human agency and full automation as the extreme ends, what are the other possible modes of machine assistance? As such, the question that we want to find out is how humans make decisions with machine assistance in challenging tasks. And here, we want to emphasize the notion of challenging tasks because in recidivism prediction, judges do not know for sure if the person would commit a crime again or not. But unlike in an object recognition task, I'm pretty sure most of you here would be able to recognize if a cat exists in a picture or not. Green and Chen explores recidivism prediction as a case study with a machine in a loop as well, and their talk is later in the afternoon. But here, our focus is on exploring possible modes of machine assistance. So we propose a spectrum between full human agency and full automation. Ideally, we hope that humans can perform well with minimal machine assistance, such as only showing explanations without revealing the predicted labels. Explanations here may be highlighting important information from the perspectives of machine. And as you can see on the slide, moving towards the right of the spectrum, the influence of the machine becomes greater and greater. First, we show predicted labels, then we show predicted labels with explanations, and last, we show predicted labels and statements suggesting that the machine performance is high. We use deception detection as a case study for the following 3 reasons. Firstly, deception detection is a challenging task for humans, as it has been proven many times in research that humans' performance are just around chance, which is around 50%. In our project, we used the linear SVM model as our machine, and its performance is 87%. Secondly, deception detection does not require judges in our task, and judges are expensive, so. And lastly, it will be useful for us to discern deceptive and genuine reviews while reading reviews online, since most of us read reviews on a weekly or even daily basis when we want to purchase stuff on Amazon. In our project, we defined human performance using accuracy as the percentage of correctly predicted instances. Before moving on to the results of our experiment, which is the most exciting part in my opinion, I would first like you to predict the actual label of a hotel review. So it's either deceptive or genuine. A deceptive review is defined as a review that is written for compensation and they do not actually experience what they wrote in the review. And genuine review is defined as reviews that have been written by people who have actually stayed in the hotel. So here's the review, and I'll be reading along with it, so you can just follow the pace. I would not stay at this hotel again. The rooms had a foul odor. It seems as though the carpets have never been cleaned. The neighborhood was also less than desirable. The housekeepers seemed to be snooping around while they were cleaning the rooms. I would say that the front desk staff was friendly, albeit slightly dim-witted. I'll give you a couple of seconds to ponder over it. And this review is just going to repeat the other 2 times. So due to time constraints, I'm going to move on. Okay, now let's move on to the second configuration. It's the exact same review, but now you can see highlighted words on the review itself. Words that are highlighted are important words determined by the classifier. The darker the blue, the more important the word is. So you have a couple of seconds to think about your decision. All right. Now we'll move on to the final activity. You may observe that the machine tells you the review is predicted to be deceptive. Now, a show of hands, who thinks the review was deceptive? And who thinks it's genuine? I think we have more deceptive than genuine in this crowd. The actual review label it's actually deceptive, but it's okay if you were to get it wrong because deception detection is a difficult task, so don't blame yourself too much. All right, now we'll move on to the experiment side. We want to find out how people generally make decisions with these machine assistants. So firstly, we want to find out if explanations alone can improve human performance. From our results, explanations alone slightly improve human performance, and explanations here refer to feature-based explanations and example-based explanations. Feature-based explanations are explanations where features are highlighted, as you have seen earlier, and example-based explanations are just explanations that are similar reviews in the training data that are given as examples on top of the to be predicted review. We see that highlight and heat map significantly improves the human performance over control, but overall the improvement is still pretty limited. Next, we introduce predicted labels. We expect that people do better than showing only explanations, but the question now here is how much better, how big the performance gap will be. Our results show that predicted labels are more effective than showing only just explanations. In fact, human performance improved drastically with predicted labels and explicit statement of machine accuracy. And you have to note that the best performance is still worse than machine performance, so humans do not always follow machine predictions. So there's a trade-off between human performance and human agency. When there is higher human performance, it's accompanied with more machine assistance, and lower human performance with less machine assistance. And since showing predicted labels are necessary for sizable human performance improvement, we want to find out if showing explanations coupled with these predicted labels is able to moderate this trade-off between human agency and human performance. And our results show that the predicted labels coupled with explanation would induce a similar effect as compared to predicted labels and the statement of machine accuracy. I'm going to speed up quite a bit because I think I'm running out of time. But for the remaining of the presentation, I would like to change gears and examine the levels of trust people place on machine predictions when predicted labels are available. And we define trust as the percentage of instances where humans follow machine predictions. From our results, we find that explanations, particularly feature-based explanations, help to increase trust on machine predictions. And we also find out that humans tend to trust machine predictions more when the predictions are correct. One possible hypothesis is that humans may be able to differentiate a difficult instance from, therefore entrust the machine list. So in the rest of our paper, we find out if human judgment changes when we vary the statement of machine accuracy. For instance, instead of 87%, we say that it's 50, 60, or even 70%. And we also did analysis on heterogeneity between participants. We found out that if you were to write review on a weekly or a frequently basis, you're better at detecting deceptive reviews. Here are the three major takeaways. I may be speeding too fast, but you can just remember these three major takeaways. The first one is explanations alone slightly improve performance. And secondly, there's a trade-off between human performance and human agency. And lastly, when you couple explanations with predicted labels itself, it is able to moderate this trade-off between human performance and human agency. Our public demo is available at deception.machineinaloop.com. Thank you.
So can we have all of the speakers back up? And if there are any questions, there are microphones on either side. Over here, I think you got it first.
I have a question for Chris and Berk primarily. Is there a limit to the canonical problems that we are talking in this field, like loans, the data sets, the benchmark data sets that we're studying here, insofar as the variables tend to be interpretable by humans? So as soon as you start to use variables, gyrometer, web tracking data, things that you can't actually semantically show, either in terms of recourse or explanation, what do we do and how do we address those kind of methods in maybe real-world, really high-dimensional problems based on all sorts of abstract data that's being used to infer things about people?
Yeah, I mean, I think, the answer is more machine learning, basically. So you can learn what are semantic categories, what ways to describe things to people that they can understand and is meaningful. So, of course, if you've got a Fitbit, for example, and you want to know, okay, why am I not walking 10K a week or whatever? And what it might say is that, if you'd waved your arm 1,000 times more in these different times across the time period, then I would have thought you had. And this is useless. And what you actually want is an explanation that turns around and says, well, you sit down for at 7 p.m. every day. If you went for a 15-minute walk then you would have made it over the limit. And it's this kind of learning what people actually want from an explanation and then somehow having a mapping to that from the raw data, which lets you give meaningful explanations that can be possibly actioned on, or at least people can understand the system through. Do you want to?
Yeah, I mean, to add to that, I'll say, in these settings that you're talking about, there's a good chance that there might be something that's going wrong with the algorithm that you could detect, but that you'd overlook because you just don't understand the variable that you see. There's an example in our paper where, for instance, we encoded a variable in a certain way. It was the last payment, has this person ever missed a payment versus has this person ever missed a payment in the last year? And just that small difference prevents someone from having recourse. So in that case, I think just providing an explanation without that sanity check of can someone flip their prediction? You run the danger of just kind of overlooking that through confirmation bias. Thanks.
Thanks.
I think if we go over this side.
Hi, my question is also, I think, for Berk and Chris. So my concern when it comes to things like recourse or providing counterfactuals to tell people what they could change is that there's sort of a risk of putting all the onus on the individual to change things about themselves, and in the process maybe missing larger structural issues. And I see that if there's something obvious, like you're telling a bunch of people to change their race, that's obvious there's something wrong. But I imagine there might be more pernicious things where you're sort of telling one group of people that they all have to ask for slightly less money than another group, and by giving them something that's actionable, you sort of make that type of bias more acceptable. So I was just wondering what your thoughts on that were.
Do you want to go first this time?
No, I agree with that. I mean, like when you end up producing a flip set and sending that over to someone, it says, oh, this is what you can do to change your prediction. There still might be something that's fundamentally wrong. Like, I don't know, men might have to work less than like women to flip their prediction and get approved for a loan. And to some extent, maybe with our work, you could mitigate that through an audit and look at how difficult things are. But to be honest, that's not the level of contestability that like a lack of recourse would show. And I think that that's kind of like the work that we need to do in hammering out like very specific notions of harm with precise definitions that aren't like subject to debate.
Yeah, so I think your question kind of puts the thumb on the difference between explainability and recourse, right? Because there is still this explanation that, oh, if you change your race and maybe done something else as well. So it would flag up for people, there is this bias in the system. So in some sense, I think this means recourse is what companies want to give people. I think these are generally the safe answers that you can trust to hand out to the public without causing a riot. While explainability, like a good explanation, I think quite often will make people angry. And it will tell them that there's something in the world that needs to be changed.
Can I actually say something? Yeah, I think this point is really good, and while I think agency is super, super important to ensuring these decisions, because the classifiers we normally use are not causal in the first place, as we question whether we want like to put this sort of burden on individuals, we have to think about what kinds of like behavior we're incentivizing for individuals. So for this like loan classifier, maybe the right way to actually change your decision is to like open up 3 more credit cards, and that like changes your decision. Doesn't make you a more trustworthy person. It's like questionable. So by putting more like saying, here's how you can change your decision, you also want the incentivized behavior to actually be useful for that individual rather than simply like being high, like useless cost things. Yeah.
Hi, my name is Roel from the AI Now Institute. I have a question for Vivian about, first of all, thank you for bringing more empirical work to this community, which I think is really valuable and much needed. I have a question about the data collection, especially for constructing the deceptive explanations. So I was wondering if there's any kind of regularity in there through the construction of that data, or can you kind of elaborate a bit on how you collected it or how you constructed that data?
Thank you for the question. We actually didn't construct the data set. The data set is from the paper written by Ott and al. But it's a Cornell data set. I think you can just look it up. And to tell you more how they constructed the data set, the deceptive reviews are written by Amazon Mechanical Turkers, and they would vet through manually and see if it passes. And because deceptive reviews are on average, they have 150 characters. If they are written less than 150 characters, they are rejected. And if they take less than a certain number of time, they would reject that thing as well. So there's quality control in the data set. But if you're interested, you can look up that paper.
Thank you.
Hi, I'm Hua Zheng from University of Virginia. I have a question for Berk. Regarding your paper, your assumption basically your paper works under a linear model, and I have a question regarding the assumption that do you assume the features you are working on are independent from each other? And for example, I have a question. For example, like if a person has, for example, I have 3,000 credit loans, and I have, for example, 5 credit cards. Would it be somehow easier? Say your algorithm suggests that I reduce the credit debt from 3,000 to 1,000, or I reduce the number of credit cards I have from 5 to 2. Would it be an easier solution? Say I reduce my number of credit cards from 5 to 3 and reduce 1,000 from 3,000 to 2,000 credit debt because they are correlated. The features are correlated. And so this is the first question is about the linear case. And would you think it would be also generalizable to the nonlinear model? Thanks.
Yeah, let me answer the second question first. Yeah, it's generalizable to nonlinear case. It's a little trickier, but that's something that we're working on. But the underlying machinery, we've designed it so that it will handle nonlinear case. And that's maybe later this year. The second thing is what you're saying, that's kind of why we chose like an integer programming framework to deal with this. Basically, there are cases where you could either change one variable or another variable, but not both, and those are logical constraints that you can just add into the integer program. The experiments that we're running, we don't make that assumption. And also, I think the costs themselves, it doesn't reflect this joint, like that joint changes could be easier or harder. So yeah.
Okay, I think that we will have to take the rest of the questions offline. I noticed a couple of interesting ones on Slack as well. But in the interest of letting people recaffeinate, please thank all of the speakers with me.